So in this video I'm going to look at a few of the past paper questions to do with rates. I'll cherry pick a few of these out, do the more difficult ones, bring your attention to some that examiners ask frequently, which students find fairly challenging. Anyway, let's get going. So the first one here is a question about the reaction of bromine, okay, and that is bromine reacting with methanoic acid. Okay, now first couple of questions are pretty straightforward. Make sure you've learned your CCEA experiments for those. That's really all they're after there. If we go down below, it says, use the graph below to determine the time taken for the concentration of bromine to decrease from 0.1 to 0.05, 0.5. Right, now, if we do that, so we're going from 0.1 to 0.05, that time there is 190 seconds. And then we're going from 0.05 down to, let me get my half of that, 0.025, okay, and that time there, we'll call that time 2, is also 190 seconds. And it asks us to use that to work out the order with respect to bromine. So what you should know there is that this is called half-life. A half-life is the time taken for the concentration to fall by half. So in other words, 0.1 to 0.05 and 0.05 to 0.025. And the half-life there is constant. And when you get a constant half-life, in this case 190 seconds, okay, that tells you that it is indeed first order. So you've got to use the graph there to work out that time. It was indeed 190 seconds, and suggest the order. Well, it's very simply first order. Okay, right, then this question here always causes a bit of difficulty. Suggests why a large excess of methanoic acid is used to investigate the order with respect to bromine. So if we go back up to the question, the bromine is reacting with, tells us now, a large excess of the methanoic acid. And the reason why we do that is we want to make sure that our bromine in this particular instance is our limiting reactant. That is the thing that is controlling the rate of the reaction. And if we have our methanoic acid in a large excess, what we can really say is that the concentration of that essentially remains constant. It doesn't change. It might change a tiny bit, but relatively speaking, it doesn't change. Okay, and that's when we're investigating the order with respect to, in this case, bromine. Ideally, what we want is the concentration of the other reactant to remain constant. Now, obviously, the other reactant has to react. So the only way that we can really make it constant is if we use it in a very large excess. So we'll have a look at this one. It's a very, very simple one, but it does come up a lot, and sometimes you just need to be shown how to do it in the first place. So it says here, you've got to say, how will the rate of the reaction change if the concentration of all of the reactants are doubled? Right, so the rate equals K, which is a constant, so I'm going to leave that out, upon A and B concentration squared. So very simply, if you think back to, I think it was maybe the third video that I did, I kind of covered this, and you should be able to apply the method that I used there maybe to this. So all you do is you sub in the relative changes of the concentration of A and B. So they both doubled, so I'm just going to put a 2 in there, multiplied by 2 again to the 2. So therefore, in other words, it's 2 times 4, so the rate will overall change by a factor of 8. So the answer is, of course, C. Dead simple. Okay. So this question here was a difficult one, and it actually wasn't that tricky, but the way it was presented to students in the paper made it a little bit of a challenge. Okay, and really threw students off because it wasn't in the sort of standard format that a rates question is. So what we've got here is a compound called procaine. Okay, it's an anesthetic essentially, and that procaine undergoes enzymic hydrolysis in the kidneys to form a thing called para-aminobenzoic acid. That's the product of the hydrolysis reaction in the kidneys. Now, it tells you up here, and this is a clue for what we do later, that para-aminobenzoic acid is a weak acid. Okay, so don't ignore these little bits of text at the start of a question. There is important information in them that you would need to pick up on. Okay, it'll help you later on, I promise. Okay, so we did a investigation, kinetics investigation, or kinetics or rates experiment, whatever you want. Okay, and it was done at 20 degrees Celsius. I think that might be of some importance later on, but we'll highlight it anyway. Okay, and that is all represented in graph 1. Okay, and then from graph 1 we produced graph 2. Okay, so use a graph to deduce the rate of PABA when 30 seconds has elapsed. So the rate of PABA is only given in graph 2. So what we've got to do is we've got to go to graph 1, we've got to go to 30 seconds, we've got to go up and over and across, and that brings us to a concentration of 0.2 moles per decimeter cubed of the PRO, the protein. We bring that down to here, to our 0.2. We go up and we go across to there. And that gives us our rate of PABA when the concentration of PRO is 0.2 and the concentration of PRO is 0.2 after 30 seconds. Okay, so our answer there, just reading it sort of off the graph myself, 0, 0, it looks about 0.005 moles per decimeter cubed. So that's how you go about that. Okay. The next question asks us, well, how do you make graph 2 from graph 1? Well, if we look at the equation up above, and this is important because it just does, our PRO and our PABA are in a 1-to-1 ratio. So when I go to my graph here and I take a tangent and I take another tangent and I take another tangent, that is given me, okay, so remember concentration versus time gives me tangents, gives me the rate. And that has given me the rate, okay, at which the PRO is decreasing. Okay, the PRO is being used up, if you like. And it gives me that in moles per decimeter cubed per second. Now, if I then make the connection between PRO and PABA, that they are 1-to-1, that means that the rate at which PRO is decreasing has to be equal to the rate at which the PABA concentration is increasing. So if I take my rate from graph 1, and that tells me the rate at which PRO is increasing, that is essentially the same as the rate at which PABA is increasing. Okay? So that's how that was worked out. You basically took tangents, you plotted tangents against concentration, okay, and that gave you your second graph. And then we had to deduce the order with respect to protein from graph 2. Well, we can see that the rate and the concentration are directly proportional. We should know from, I think it's the second or third video, I can't quite remember, if they're directly proportional, that it must be first order. Assuming the order with respect to the enzyme is 0, write the rate equation for it. Okay, so our rate equation therefore is rate equals PRO square brackets to the 1. Okay. And we had to then calculate the rate constant for that, and we had to state its units. Right, so let me tidy this up a little bit first of all, and we'll work that out. Okay, so we were rate equals K upon the concentration of PRO. So what I've done on my graph, I took a point in the graph here which lay right on the 0.3. So my concentration is 0.3. Okay, my rate at that point is 0.008. Okay, and that's K. So K equals 0.008 divided by 0.3. Okay, my units would be moles per decimeter cubed per second, top line, and bottom line would be simply moles per decimeter cubed. Cancel, cancel. My units will be S to the minus 1. So 0.008 divided by 0.3, whatever that is, and the units are S to the minus 1. Okay. The next one says the reaction catalyzed by the enzyme and the initial reaction solution is neutral. Big clue. Suggest how the rate of reaction could be followed. Now, if we go back up to where I picked out earlier, it tells us that the product is a weak acid. So you can follow this in two ways from your CCEA practical methods. You can either follow up by using a pH meter and turning that into concentration of the acid, okay? or you can quench the reaction. Okay, remove probably 25 cubic centimeters and titrate that against a standard solution of a weak alkali, of a strong alkali. Usually sodium hydroxide is what we would use. And you will use an indicator there. Phenolphthalein indicator would be appropriate because it's a weak acid, strong alkali. Okay, you must say standard solution of strong alkali. I think you did anyway. And you must not use methyl orange because that would be an inappropriate indicator for a weak acid, strong alkali. Okay, so that's what you do there. Let's have a look through and find some other tricky ones. So this question here goes back to the 5th video, which was about mechanisms, and you've got to work out the orders with respect to propanone, hydroxonium and iodine. So the key thing here is we have a slow step here, and in our slow step we have 1 mole of the propanone, so that must be first order. So we can either go A, B or D for that one. My hydroxonium ion is also in there. There's only one of them, so that means I can either go A or D, so I have ruled out now B. And finally, there is no iodine in the slow step, so iodine must be 0 order, so I can rule out that. So my answer has to be A. We'll just have a quick look at this one. This is going back to the one we did earlier, where we had our bromine and our methanoic acid, and it asked you to suggest an experimental method. So this is going back to video 1 that we watched. The experimental method would be the colorimetry. Look, this is worth 6 marks, so make sure you learn your colorimetry very well. The reason why it's colorimetry is because bromine here starts off at a browny orange colour, and as it goes through the reaction, that colour fades. Okay, everything on this side here is colourless. So the quicker the colour fades, essentially the faster the rate of reaction, or you would describe your colorimetry experiment there. Here's another one of our mechanism questions. Okay, so it gives you the stoichiometric equation and it gives you the rate equation. So rate equation is y to the 2, so the slow step must contain 2 y's. Well, let's see where we go here. Slow step here, no, contains a xy. Slow step here, this looks promising, okay, contains 2 y's, that can't be the slow step in C, and that can't be the slow step in D. So I don't really even need to look at this step here, to be honest with you. I've already got my answer from what was in the slow step, which is, of course, B. Have a quick look at that one, pause the video if you want. So the answer to that would again be colorimetry. We've got iodine, which is a coloured substance, brown in solution, and it fades to a colourless solution. This is quite a good question here. Easily worked out, but it's good to be exposed to it, so I'll talk you through it. I'm talking about question 5 here, where it asks you for the overall equation. So let's have a look. We've got our, if we look at our H2BO3 minus, that is made there, and then it is used up, so that'll definitely not be in our final equation. Let's try and find anything else where that applies to. Br2O2 also made up, then used up, so that is not going to be in our overall equation. Anything else in there that's being... No, I don't think so. So let's look, we've got BrO3 negative. We've only got one of those, so I'm going to rule out C and I'm going to rule out D. Hydrogen ions, I have 2 reacting there and 4 reacting there. I have none being made on the right hand side, so I need 6 of those. Let me see. So that gives me, well, that doesn't help me at all because both A and B have 6 hydrogen ions, so I'm going to have to go and find the bromides. I have 1 bromide reacting there and I have 4 bromides reacting there. None are being made on the right hand side, so there's 5 bromides reacting in total. Okay, so the answer has to be B. Here's another question about mechanism. So we're looking for the steps that are appropriate for up above. Now the little trick that they've tried here is to put X in at 0. So in the slow step, X is 0, so it is not involved in the slow step. And we have Y2, so we're looking for something with a slow step with 2 Y's in it. So let's have a scan down. The only thing I can see there, D, is a slow step with 2 Y's. Let's check everything else is correct. And we have 1X then reacting here, that's fine. We have this Y2 being made here but being used up here to give us XY2. So everything correlates with the rate equation, everything correlates with the stoichiometric equation. The answer has to be D. Okay, so I've gone through the past paper questions there, guys. There was a video 4 which had a lot of past paper questions on it. Video 3 had a lot of just questions on it. They weren't past paper ones, but they were very similar. And I've done 15 minutes there on past paper questions. So hopefully by now you have a really good idea of what's going on with regards to your rates and your kinetics. So just work away at the questions, check them, make sure where you're going wrong. Okay, if you're unsure where you're going wrong, make sure and come and see me. Okay, thank you.